Getting to Mars with today's rockets takes about 7 months. 7 months trapped in a metal can, exposed to radiation with no way to turn around. NASA thinks it has a way to cut that time dramatically, and the answer isn't a bigger rocket. It's a nuclear one. For the first time in over 50 years, the United States has been building a nuclear-powered rocket engine designed to send humans to Mars faster and safer than ever before. Today, we're breaking down exactly how it works, why it's such a massive leap over what we're using now, and what it actually takes to fly a nuclear reactor into space. Every rocket that's ever carried humans, Apollo, the Space Shuttle, Falcon 9, Starship, runs on chemical propulsion. You mix a fuel with an oxidizer, ignite it, and the explosion pushes you forward. It works, but it's inefficient for the distances Mars requires. Chemical rockets get you a certain amount of thrust for a certain amount of propellant, and that ratio, called specific impulse, hits a hard ceiling. To go faster, you need exponentially more fuel, which makes the spacecraft heavier, which needs more fuel to move that weight. It's a spiral that limits how fast we can realistically travel through deep space. And speed isn't just about convenience. A shorter trip to Mars means less time astronauts spend soaking in cosmic radiation outside Earth's protective magnetic field. It means less food, water, and oxygen that needs to be carried. It means a smaller window where something can go catastrophically wrong. This is exactly the wall NASA hit decades ago, and exactly why nuclear propulsion never fully left the conversation. So here's the concept, and it's simpler than people expect. A nuclear thermal rocket, or NTP, uses a small nuclear reactor, powered by fission, the same basic process used in nuclear power plants, to generate enormous heat. Instead of using that heat to boil water for electricity like a power plant does, the rocket runs liquid hydrogen propellant directly through the superheated reactor core. The hydrogen instantly turns into an extremely hot gas, expands violently, and gets shot out of a nozzle at tremendous speed. That's your thrust. The advantage is efficiency. Nuclear thermal engines can be roughly 2 to 5 times more fuel efficient than the best chemical rockets, meaning a spacecraft needs far less propellant to hit the same speed, or can go dramatically faster with the same amount of fuel. Less fuel mass means more room for crew supplies, scientific equipment, or radiation shielding. This isn't untested theory either. Back in the 1960s and early 70s, NASA and the Atomic Energy Commission ran an entire program called NERVA, Nuclear Engine for Rocket Vehicle Application, and successfully test-fired nuclear thermal engines on the ground multiple times. NERVA proved the physics worked. What killed it wasn't the technology, it was funding. When NASA's post-Apollo budget got slashed in the early 1970s, NERVA was canceled before it ever flew. For 50 years, that's where things sat. That changed when NASA partnered with DARPA, the Defense Department's advanced research agency, on a program called DRACO, the demonstration rocket for agile cislunar operations. The plan split responsibilities cleanly. NASA focused on developing the nuclear reactor and engine itself, drawing on decades-old NERVA-era research combined with modern materials science and reactor design. DARPA focused on the spacecraft that would carry it. Lockheed Martin was brought on as the prime contractor to design, build, and test the demonstration vehicle, and General Atomics also contributed to the reactor design work. The goal was audacious: launch an actual nuclear reactor to orbit and fire it up in space, something the United States had never done before. Ground tests are one thing. Actually operating a fission reactor for propulsion hundreds of miles above Earth, in real orbital conditions, is a completely different engineering challenge. From radiation shielding to how you manage a reactor that has to survive launch vibration and the vacuum of space. If successful, DRACO would have marked the first live demonstration of a nuclear thermal rocket engine operating in space in history. A genuine milestone, more than 50 years in the making. Zoom out. And this technology isn't just an engineering flex. It's core to NASA's actual roadmap for sending humans to Mars. NASA's own timeline for crewed Mars missions points to the late 2030s or early 2040s, And one of the biggest open questions has always been propulsion. A nuclear thermal engine, more efficient than anything currently flying, could meaningfully shrink transit time between Earth and Mars. Every month shaved off that trip is a month less of radiation exposure, a month less of psychological strain on a crew millions of miles from home, and a month less that something needs to go right without room for error. It also changes the shape of Mars mission planning. Faster transit could open up more flexible launch windows. Right now, Earth and Mars only align well enough for an efficient trip once every 26 months. A faster propulsion system doesn't eliminate that constraint, but it gives mission planners more breathing room within it, and could make return trips less punishing for the crew involved. This is why, even though NTP has strong competition from things like SpaceX's Starship and other in-space propulsion concepts, NASA has continued treating nuclear propulsion as one of the key technologies on its long-term Moon-to-Mars roadmap. Let's address the obvious concern. Isn't launching a nuclear reactor into space dangerous? It's a fair question, and NASA and DARPA have been explicit that safety architecture is baked into these designs from day one. The reactors used in nuclear thermal rockets typically run on low-enriched uranium, nowhere near weapons-grade material, specifically to reduce proliferation and safety concerns. The reactor also isn't switched on until the spacecraft is safely in a high enough orbit, well away from Earth's atmosphere, specifically to minimize any risk in the event of a launch failure. The United States actually has a long, quiet history of flying radioactive material safely. Plutonium power sources have flown on missions like Voyager, Cassini, and the Mars rovers, Curiosity and Perseverance for decades without incident, because those systems are engineered and tested extensively for launch failure scenarios. Nuclear thermal propulsion engineers are working from that same safety-first playbook, just applied to a much more powerful reactor system. That doesn't mean the challenge is trivial. It's a genuinely hard engineering and regulatory problem, which is part of why this technology has taken so long to get this far. Here's an important update, because the story doesn't stop with the plan. In 2025, DARPA made the call to cancel the DRACO program, and it was left out of NASA's fiscal year 2026 budget request entirely. The stated reasoning: the dramatic drop in launch costs driven largely by reusable rockets like SpaceX's Starship changed the cost-benefit math, and nuclear thermal propulsion was judged too expensive and too far out for the near-term Mars transit alternatives now on the table. That doesn't erase what was built or learned. The reactor research, the safety frameworks, the Lockheed Martin spacecraft design work, all of it still exists as a foundation NASA or a future program could pick back up. But as of today, there is no active, funded nuclear rocket flying toward a launch pad. The dream isn't dead. It's on the shelf, waiting for the budget, the mission, or the moment that brings it back. For half a century, nuclear propulsion has been the technology that could get humans to Mars faster. Proven on the ground, never flown in space, always one budget cycle away from happening. Whether it's DRACO coming back, a new program picking up where it left off, or something else entirely, the physics hasn't changed. If we want to shrink the trip to Mars, nuclear power is still the most credible way to do it. If you want to know the moment this technology gets a second life, subscribe, because when it happens, we'll be covering it first.